Today's lesson's on implicit differentiation. Implicit differentiation is used to find the derivative or the slope of a curve which is not a function. Something that's not a function that you guys are all familiar with is a circle. So we'll be able to find the derivative of the circle. It can also be used for functions that are in explicit form. Most of the explicit forms that you guys are familiar with are just y equals equations. So let's go ahead and just talk about the difference between implicit and explicit equations. Explicit equations will be those of functions. So this one right here is a function. It's a parabola. So this is actually explicit. This one right here is of a line. It is also, if I go ahead and solve for y, explicit. On this next equation, I can solve for y, but I'd have to square root both sides. And this is also not a function, so this is considered implicit, as well as this last one. It'd be very difficult to solve for y. It's not a function, it's implicit. Here's the steps that we're going to use for implicit differentiation. The first thing we're going to do is we're going to differentiate both sides of the equation with respect to x, which means we're going to be taking the derivative of y with respect to x. So we're going to end up with a dy over dx. Remember, y prime and dy over dx are the same. I'm going to say that more times today than I even know how many times I'm going to say it, because it's so important that you guys know that y prime and dy over dx are exactly the same. The second thing we're going to do is we're going to collect all our all our y primes on one side of the equation. Now, this is also dy over dx's, so we can say we're going to collect all our dy over dx's on one side of the equation. And we're going to put everything without the y prime or without dy over dx's on the other side. We're then going to factor the y prime out on the one side. Remember, that's the same thing as saying we're going to factor out the dy over dx on one side. And then we're going to solve for that y prime. So our answer could read y prime or it could read dy over dx. These two things are exactly the same. I'm going to show you that in the first problem. It's your choice whether you use a y prime or dy over dx. So we'll go ahead and do this, find this derivative. Normally, every derivative we've done so far has always been a y equals equation. Notice how this one does not have y equals. We are going to take the derivative of this, x cubed, by saying, okay, this is an x. So the derivative of x cubed is 3x squared. Plus, the derivative, oh wait, this isn't an x. So I've got to take the derivative of this, y, like normal, bring this out in front, rewrite the y, and lower it by 1. But since this isn't an x, I need to add on a y prime. Then we're going to say this equals 0, because the derivative of 64 is 0. Now let me show you the derivative of this if I would have used dy over dx's. So 3x squared plus 3y squared dy over dx equals 0. Notice the only thing different is I put a dy over dx here and I put a y prime here. Remember, dy over dx and y prime mean exactly the same thing. So that was step number 1, differentiate both sides with respect to x. The second thing we're going to do is collect all our y primes on one side of the equation. I only have one term with a y prime. It's right here. We're going to leave that on the left-hand side, and I'm going to move the 3x squared to the other side. That makes my equation read 3y squared y prime equals negative 3x squared. I really cannot factor out in step number 3 the y prime because there's really only one term. So I'm just going to solve for y prime. So we're going to divide by 3y squared, divide by 3y squared, and I end up getting y prime is equal to, my 3's cancel, I get a negative x squared over y squared. This will allow me to plug in for any point and find the derivative at that point. Remember, derivative means slope of the tangent line to the curve.